Hi, I'm Dr. Tim Komar, and today we will discuss an example involving the continuity and differentiability of a piecewise defined function. This video is appropriate for students in first semester calculus and students in AP calculus courses. The video is organized by first showing some background information and then getting on with the example. For those who just want to get to the example, please do feel free to skip ahead. So we'll quickly review a definition of continuity here. So informally, a function f is continuous if its graph can be drawn without lifting the pencil from the paper. We can state this as follows here. Well, a function f is continuous at the point x equals a if the limit of f of x as x approaches a is equal to the function value f of a here. And we can see that nicely in the picture over here. Encoded in this definition are the following conditions for the continuity of the function f at x equals a. First of all, the function value has to exist, the limit has to exist, and they both have to be equal to each other. And again, this is what's also shown here in the picture. I'll quickly remind you about the connection between one-sided limits and limits. So let's say we have a function that is defined on an interval containing x equals a, but not necessarily at x equals a. Then the limit of f of x as x approaches a equals the number L if and only if the left-hand limit as x approaches a and the right-hand limit as x approaches a of f of x are both equal to L. So we can also connect continuity to one-sided limits. So again here, let's just say we have a function f that is defined on an interval, this time containing x equals a. Then f is continuous at x equals a if and only if the left-hand limit of the function as x approaches a and the right-hand limit of the function as x approaches a are both equal to the function value f of a. And now for a quick review of differentiability. The derivative of a function f at x equals a is the limit denoted by f prime of a, which is the limit as h goes to 0 of the difference quotient f of a plus h minus f of a divided by h if the limit exists. And if f prime of a exists, we say that f is differentiable at x equals a. Geometrically, a function is differentiable at x equals a if the graph of y equals f of x has a unique non-vertical tangent line at x equals a. Here we have a graph of a function in red. We have a point here on the graph where x is equal to 2, and we have the tangent line drawn here in green. So using what we know about one-sided limits, we know that the derivative f prime of a exists if and only if the left-hand derivative f prime minus a equals the right-hand derivative f prime plus of a here, where these two one-sided derivatives are defined analogously to the way that we define the derivative itself, except that we take left-hand and right-hand limits accordingly. So this is going to be key to our example. And here again is the relationship between differentiability and continuity. Simply stated, differentiability implies continuity. Stated as a theorem here, if f is differentiable at x equals a, then f is continuous at x equals a. Sometimes we like to state this in terms of the contrapositive statement. If f is not continuous at x equals a, then f is not differentiable at x equals a. The second statement here is a nice way to show that a function is not differentiable if we can simply show that it's not continuous. So here's our example now. We have this piecewise defined function over here where the function is defined to be x minus 2 quantities squared on the interval from -4 up to and including -2. It's equal to -8x on the interval from -2 up to and including 1. And is equal to -2 times x plus 1 quantity squared minus 4 on the interval from 1 to 4. And we want to show that this is differentiable at x equals -2 and is not differentiable at x equals 1. So we're first just going to look at continuity at x equals -2 here. So again, if we're going to look at the left-hand limit at -2, we're going to use the appropriate definition of the function on the interval where x is less than -2 over here, and that's the x minus 2 squared. The limit here comes out to be 16, which is the same as the function value. Pretty straightforward to compute. We can also compute the right-hand limit here, but if we're computing the right-hand limit, we're going to need to use the -8x as our definition of our function here. And again, we get a value of 16, which equals the function value, which equals the left-hand limit. Our function is continuous at -2. Now we're going to look at differentiability at x equals -2. And we're going to do this by looking at the one-sided derivatives here. So if we're going to calculate our left-hand derivative at -2, again, we're going to be taking a limit as x approaches 2 from the left-hand side here, and we're going to use that x minus 2 squared definition for our function here. Function value is still 16. Pretty straightforward to do a little simplification here, and we can compute that the limit is going to be -8. If we're going to compute the right-hand derivative at -2, we're going to need to use that -8x definition for the function there. Function value is still 16, and the limit is easily shown to be -8. So since the left and right-hand derivatives at -2 are both -8, the derivative itself at -2 exists and, of course, is equal to -8. Now we're going to look at x equals 1 here. So if we're going to compute the left-hand limit of the function at 1 here, we're still going to need to use that -8x definition here, and that's going to be -8, which is also equal to the function value. But if we're going to compute the right-hand derivative, we're going to have to use the appropriate definition of our function over here, and that limit comes out to be -12, which is not equal to the function value or the left-hand limit. So the function is not continuous at x equals 1. Now, using that corollary from before, since f is not continuous at x equals 1, it is not differentiable at x equals 1. And this is enough to be done with the example over here. But for those interested, here is a closer look. Yes, we can compute the slopes of tangent lines approach -8 as x approaches 1 from the left using derivative rules, and that the left-hand derivative we can directly calculate is going to be -8. And also, yes, slopes of tangent lines at values of x that are slightly greater than 1 are also going to be -8. The problem lies in that right-hand derivative at 1 does not exist. Well, now we are going to attempt to compute the right-hand derivative of 1 and see that it does not exist. So as we compute this, again, we're going to be computing the limit of a difference quotient as we're only coming in from the right-hand side. And as we're coming in from the right-hand side here, we're going to have to use that appropriate definition of the function here. But the function value is still -8 at 1. So we simplify this a little bit, and we can pretty much see from this last expression down here that the right-hand limit here does not exist. The values are going to be decreasing without bound. That's why we write -infinity here, which means that it doesn't exist. If we want to look graphically at what's going on over here, what we just saw, again, is here where we have that jump discontinuity here at 1. Again, the function value here is at -8, where this red dot is over here. And this is an example of a secant line on the right-hand side uh, of 1 over here. And we notice that the slope here is going to be negative. And as the values of x get closer and closer to 1 from the right-hand side here, eventually this is going to approach a vertical line. And again, it's going to have a slope that is unbounded in the negative direction. If you want to look at our nice little point over here, here was at -2, where number 1, the function was continuous, and it's also differentiable. The green line here is the tangent line at -2. In fact, it's exactly equal to the function on this interval here between -2 and 1 over here as well. So it looks green here rather than red. So thank you very much for listening. I'm available for tutoring and hope to see you soon.